Okay, so today I want to start to talk about everything to do with priority queues. I want to talk about priority queues and also how they're implemented, and we'll also take a look at some source code at the very end, maybe next time. So along with this, we're going to talk about also heaps. Heaps because they're very related, and let's start by looking at the outline. So priority queues are a big topic, and that's why I have divided this talk by uh, some smaller ones. Okay, so we're going to start by looking at what is a priority queue, and what is a heap, and also we're going to look why they're useful. We're going to look at when and where they're used, and also some common operations with them. We're going some complexity analysis this time, and next time I'm going to talk about how to turn a min priority queue into a max priority queue, and some implementation details about syncing and swimming and adding elements and removing them, and next time about code implementation. Okay, so now let's discuss this. So firstly, let's look at let's look at what a priority queue. What is a priority queue? So a priority queue is an abstract data type. Abstract. So that means that it can be implemented using different data structures and different ways. So that operates similar to a normal queue, to the simple queue, but so every element here each element has a certain priority. So a priority of the elements in the priority queue determines the order in which they would be removed from the priority queue, or peaked. Also, so
PQ.
now, dequeued. We can say this. Yeah,
Yeah,
we
PQ.
can say here. Yeah. Also, a side note I would like to remark is that priority queues support only comparable data types, so we can insert only data that can be ordered in some way. So from least to greatest, or from greatest to least. In other words, to put it differently, we have to assign some properties to each element. And now let's look at an example. So let's suppose that all these values that we have here, all these values are inserted into a priority queue with an ordering imposed on the numbers to be from least to greatest. So, in other words, the smaller number here, have higher priority of the bigger one, so they will be removed first from the priority queue as needed. Okay. And now, I want to do an example of how to show how a priority queue works when we are inserting and polling, or adding and removing and polling values. So the poll operation removes the element with the highest priority in the priority queue. So as we know, here the priority, the smaller elements have the bigger priority. So the element with the higher priority happens to be 1. So we are removing it, and we're removing it from the queue. And next we want to add 2, and we want to now to pull the next element and the smallest element in our priority queue, and that is here the 2, the element with the we can say here node with the value of 2 that we have just added, and we are adding 4, and then we want to pull the smallest number with the greatest priority, that is 3, and we want to add 5, 9, and next we just pull the rest elements, the rest of the numbers, 4, then 5, 8, 9, 14, and 22. So it turns that here we pulled every number from the queue and they're pulled in an ordered sequence, in ascending order. So that is here. That is a coincidence, because they're not necessarily get an ordered sequence, because the only thing we guarantee that the next number that is removed from the priority queue is the smallest number, or the number with the higher priority, with the highest priority that is currently in the priority queue. So how does this priority queue, how does a machine knows which smallest number, which is the smallest number that the machine have to remove? So we could see at all the numbers here, and determine the smallest before the pull operation. So we can do this because we see every element. We can look at them, but how does the machine know this? So the first idea is to every time resort all the elements inside the priority queue before every pull operation. So this would be highly ineffective to resort. And if we have a lot of elements, if we have maybe thousands of elements, instead, most priority queues implementations use a heap to add and pull elements. A heap. Now let's look at what is a heap. Now, the definition from the Wikipedia is, that is a tree. That is very important. That would be very important also further, that is a tree, and that and so the tree-based data structure that satisfies the heap invariant. We're going to look at it, what is a heap invariant, a bit further, and that is also known as heap property. So if A is a parent node of B, then A is ordered with respect to B for all nodes A, B in the heap. A and B in the heap. So now I usually now let's look at what is a heap invariant or heap property. So that is the value of parent node. So if the value of parent node is, it is greater or equal to the value of the child node for all nodes here, that means that we have max heap. Or if the value of a parent node is always less or equal equal to the value of the child node, here that means that it is mean heap. So we have two binary heaps in the slide. So binary because every node has exactly two children, and the children. On the left, and the left tree here the left heap is a max heap, and the right one is a on the right is a min heap.
Okay.
So, but a follow-up question here, important question here is why we are so interested in heaps. Well, here heaps are form the some canonical underlying data structure for priority queues. So even that these priority queues are also known as the same thing as the priority queues, but by the way, they're not the same. But isn't technically correct that they're the same, because priority queue is an abstract data structure, the abstract data type. It can be implemented with other data structures also, but in many implementations, the heap is a basis of data of priority queue. Now, let's look at some heap. So we want to determine if it is a valid heap, or so we have to inspect the phone structure and to determine whether it is heap or not. So here, the answer is no, because we have a violation of heap invariant. So here, this way, we can this time we can see that that is the max heap. So the parent node is greater than the child node, and here 2 is not greater or equal to the 3, because 3 is greater than 2, and here that is not a heap, and this one is a heap because it is a tree. There are no cycles, and it also satisfies the heap invariant because every parent node is less or equal than the child node, and this time that is a min heap. Okay, now heaps. By the way, heaps are not necessarily binary heaps. There can be any number of branches. So here we have 3 branches, and here only 1, and here only 1, I think. And this is and the answer is this a tree? Is this a heap? For this one is no. This is not even a tree. We have here a cycle that contains a cycle, and heaps must be tree. And this is a tree, and this is a heap, and also this one is a heap because this is a tree, no cycles, and the heap invariant here satisfied since all nodes are equal. They're not less or not greater. And here, if the root node here is 5, that isn't a tree. That isn't a heap, because 10 is greater than 5 and 5 is less than 10. However, if we change the root to be 10, if we are turning this tree by 90 degrees, we can say, then we can say that the root here is 10, and 5 is less than 10. That means we set this we satisfied the heap priority, the heap property, So next, one moment. Let's look at when and where a priority queue gets used. Where is a priority queue used? So it is used in an implementation of a Dijkstra's shortest path algorithm. So that is very important algorithm in graph theory to find the shortest path that is very useful. That is useful in such problems, such a traveling salesman problem. That is the most effective. That is the most efficient solution for the traveling salesman, the TSP problem, and also that is the most popular places. So now it is also really handy anytime we need to dynamically fetch the next best or next worst element, and also that is used in Huffman coding. So in Huffman coding, so this is a when we want to compress some data without losing any data, without a loss compression. So we use a priority queue, and also many best first searches algorithms uses priority queue. Use many algorithms use priority queue in their implementation. So the best first search algorithms are needed to grab the next most promising node in the graph as it is being traversed. And finally, we can also see priority queues in Prim's algorithm to find the minimum spanning tree. So on a directed graph. So this priority queue is really useful in many graph theory algorithms, and so here it is very useful in graph theory. It's very important for graph theory. And now let's look at a time complexity of priority queue with binary heap with binary heap. So
Okay.
what complexity can we assign to construct binary heap construction? So there exists a method to construct them from an unordered array in linear time. So if we are given a binary array, we can construct it into a binary heap. If we are given an unordered array, we can construct a binary heap in a linear time. That's pretty fast, I think, here. And also this thing forms some basis for the sorting algorithm heap sort. That is pretty well known, pretty popular, and also pulling and removing an element from the root of the heap takes logarithmic time because we need to restore the heap invariant, which take up to log time. So we have to a bit rebuild the heap, and also picking or seeing what value at the top at the root node of our heap takes constant time, and that's pretty obvious, I think. But adding the element to the heap takes logarithmic time, since we possibly have to reshuffle the heap and by bubbling up, or also known bubbling up the value. That is the sinking and swimming operations, and we are going to talk about it a bit further. So now let's look at a complexity of naive removing and contains operation and advanced. So the naive removing from a heap takes linear time, and so we need to removing. We mean here removing some element, not a root element, but some element. So the linear here time complexity can be very slow in some in especially when we are removing a lot of terms. But we can, there, however, there does exist a way to reduce the removing time complexity using a hash table. So this takes only log n time or logarithmic time, and that is pretty that is very good because that is can be super critical and crucial, important when we are removing as much elements as we are adding. And also the naive contains operation uh, also works in a linear time complexity because we have to, in the worst case, we have to look at every element in our heap, at every node. But if we are using advanced contains operation, check contains check, with the help of a hash table that requires a lot less time, only constant time, and that is pretty good, pretty that super neat, we can say. And the downside here, the disadvantage here, the only disadvantage is using a hash table to use a contains operation is that it requires a linear space factor, and so it requires a lot of memory. But if we're doing it a lot of time, if we are checking a lot of time, we can save a lot of time by using a hash table. So, by the way, that's it. That is the end of my talk for today. Thank you.
Yeah. And thank you. You spent a lot of time on these. I like your slides. You spent. I could see you put a lot of work into your slides. I decided not a good idea to interrupt, because it makes you nervous. Okay, so yeah, I'll just look at your recording. Yeah, so
Okay.
it's just easier. Yeah, that's why I didn't talk, or I tried not to talk. So
Okay.
yeah,
Thank
yeah,
you.
but no, you spent a lot of time on your slides. Yeah, and I'm familiar with these concepts. So yeah, priority
Okay.
queues are used a lot in computer science. Yes, they are. Okay, so yeah,
Okay.
okay.